Previously, we discussed the Newton's method, and in the Newton's method, one disadvantage is that we have to know the f prime, and sometimes f prime is not easy to find. Therefore, we develop another method, which is the secant method. Now, this is what we need now, the derivative. And this derivative, according to the definition from calculus, this is the definition. And of course, we can approximate this derivative using the two consecutive approximations. If they're convergent, they should be fairly close, right? So therefore, these two values are fairly close, which means this is true. So the derivative at this point Pn-1 will be approximated using this quotient. This is the slope of the secant line passing through the points Pn-2 and Pn-1. That's why we call the new method as the secant method. We certainly try to write it better, so we swap these two, and of course you gotta swap the bottom as well. So just rewrite that in a different order, and we will use these to approximate this derivative, and as a result, that's our new formula. So simply plug this in here and simplify, and this new method is called the secant method. The geometrical interpretation of this secant method is this. You can see that we do need two initial approximations to begin the process. And what it does is this. Say suppose P0 and P1 are chosen nearby the roots P, and these are the two initial values. The secant method is to find the line passing through these points when x is P0 and this point when x is P1. So after you find this line, the intersection of this secant line, that's your next approximation. So therefore, the next approximation P2 is right here. And repeat this process. To find P3, you use most recent two approximations. In this case, P1 and P2, right? So you're going to construct a secant line through these 2 points. And then the x-intercept of this secant line will be your P3. So in this case, this will be your P3. To find P4, you need to use most recent two approximations, which means P2 and P3, right? And then through these 2 points, you construct a secant line, and the x-intercept of this secant line is your next approximation, which is the P4 in this case. Now, you do see that through the demonstration, the second comment that we have, this is actually not a root bracketing method, because you do see that P2 and P3, these two consecutive approximations do not bracket P4. So this is the geometric interpretation of the secant method. Algorithm is given. Again, you gotta modify your program code to implement this algorithm. Now let's look at this problem. We wanna use secant method to find P3 given initial values P0 and P1. I copy the problem here so that we can work on this better. In order for us to find the P3, we have to first find the P2. According to this formula, this is equal to P1 minus f of P1, and here will be P1 minus P0 divided by f of P1 minus f of P0, where the f is this function, and P0 is 0.5 and P1 is pi over 4. So plug those values in, and I'm gonna pause my videos now and then write this, plug in the numbers. Okay, so I plug in my P1 and into the formula here, and then I plug in P0 into the formula, right? And now I still need to evaluate this guy. So where my f is this. So I'll continue to plug into the pi over 4 and 0.5, these two values, into my f of x. So f of pi over 4 is equal to, using this function, this is the piece that I have. And and then f of 0.5 is equal to that. So just do some substitution, and after the algebra, the result is approximately equal to and to find my P3, I use this formula again, and I'm gonna write that out and pause the video for a moment. So according to the formula that we have, so it will be P2 minus f of P2 times P2 minus P1. So you always use previous two approximations, right? And then divided by f of P2 minus f of P1. So P2 is from my previous approximation, previous results, plug in here. So now this time f of P2, I need to use my new value here, and this is my P2 minus my P1. P1 is one of the initial values, pi over 4. Here this is f of P2 minus f of P1, and the algebra gives us this as the next approximation. So you just repeat this process to find those new approximations. Now next we are going to use Mathematica program to find a root accurate to 10 to the negative 5, and then we want to compare this with the Newton's method's result. And previously when we run the Newton's method, this is what we have. For the same problem, it took 3 steps to achieve this accuracy. What about the secant method? So I'm gonna run my program here. So I have the function, and I use these two initial values given in the problem, and after running the program, this is my result. Keep in mind, it doesn't say 5 steps because P0, P1 are given, right? The first two are given. So actually it only takes 4 steps, 1, 2, 3, 4, 4 steps to achieve the same accuracy compared to Newton's 3-step. This is pretty good, although it's not as fast as Newton's method, but it's fairly close. So this is for this, this concludes this short little video.